In today's class, we will learn about shear stresses in beams while they are subjected to some kind of bending moment. Okay, before we start the chapter, we will need to know the theories. dF dx is equal to minus W. So dF dx is equal to minus W, where this F represents shear force, X represents distance, and W represents the loading rate. Okay, and as well as dm dx is equal to F, where m is equal to bending moment. Okay, there are proofs of it, but here we will not discuss that, but in every book I think they are available. Please go through them and you will understand. Okay, so now we will start shear stresses in beams. Okay, so our job is to find out shear stress tau at any section. That is our job. Now let us have a simply supported beam with uniformly distributed load, and there are two sections. One is AB, another one is CD. Okay, now if we show it by another figure, there is a long beam, so that's why we will take sections like this, where this much is AB, this is CD, are two different sections around, and this is its neutral axis, and here the force is sigma and stress is sigma, and here the stress is sigma plus d sigma. Bending moment is M, shear bending moment is M plus dm. So these values we are talking at section AB, these values are at section CD. Okay, at CD bending moment M plus dm, and at CD the stress shear the bending stress is sigma plus del sigma. Okay, now because of these forces at a section EF, if considered at a distance of y1, from neutral axis. Okay, there is a EF plane which is at a distance of y1 from neutral axis. Okay, we will assume that the shear stress along the plane EF is tau. Shear stress along EF tau, where is EF at a distance of y1 from the neutral axis. Okay, now if we consider this much length of dx and look at its views, so these will represent the neutral axis, and this line will represent NA, sorry, this will represent, sorry, that is EF. This is NA, this is E, and this is F. Okay, our job, and this is Y1, and we have to find out the shear stress along EF. Say we name it G, we name it H. Now this length will be dx. If this is dx, the length or the distance between the two sections, so this is dx. Okay, and the width of the beam is B. Width of the beam is B. Now our job is to find out the expression of tau. Okay, and for that we will consider a cylindrical object at EF at a distance of y1, or at a distance of, say, y, at a distance of y from neutral axis. So the shear force acting on this elemental cylinder, which is having, we are considering elemental cylinder at a distance y from neutral axis, having area dA. Okay, so the length of cylinder is equal to dx. That is what we can get from this figure, and our job is to find out tau, which is shear stress at EF, or where is EF? Y1 distance above from NA. Okay, our job is to find out tau, and that's why we are considering an elemental cylinder at a distance y from the neutral axis, having area dA and length dx. Okay, and its breadth is B. Okay, now this area of EFGH, this area EFGH, area of EFGH, or the shaded area here above EF, area above EF, is considered as A. Okay, now if we look at it, then from section EB if considered, then for this elemental cylinder, the sigma is equal to m by I into y. For this elemental cylinder, from section CD we can get sigma plus d sigma is equal to m plus tm by I into y. Okay, now if we want to find the net unbalanced force on cylinder along its longitudinal longitudinal axis. This will be equal to, look very carefully, sigma plus d sigma into dA minus sigma into dA. Or from here what we can get is m plus dm by I into y into dA minus m into y by I into dA. Okay, we are putting these values only here. So what we will get? We will get net unbalanced force equal to dm by I into y into dA. So that is, this expression net unbalanced force is only for the cylinder. Now this section EFGH, this section EFGH, if we consider, is a infinite number of combination of the small cylinders. So let me clear out this situation again with a diagram. So if this is the beam, this is the neutral axis, this is B and D portion, this is dx, and this shifted little rightward because of this force dm by I into A into y, and this will be like this, and this area, cross-sectional area, okay, this is the neutral axis, this is EF, and this was G, this was H. So this EFGH can be considered as a combination of infinite number of cylinders. So for one cylinder we get the net unbalanced force is this. So for area EFGH is considered, then net unbalanced force is equal to integration of dm by I into y into dm. What we have written here, dm by I into into dA into y. So if we take this out, because I is the moment of inertia of this total area about its neutral axis. So this I is the moment of inertia of this total section about neutral axis. So that's why this I has been taken out, and dm is also constant, so it will be integration y dA, and which upon integration will be written as y bar into A, where the area is EFGH and y bar is the distance of CG of area A from neutral axis, and A is the area of EFGH, and I is the moment of inertia of the section, so the total area. Okay, so this is the net unbalanced force. Now if this is the net unbalanced force that is getting balanced by the shear force, so this unbalanced force is getting supported by the shear resistance provided at the plane which is at EF. So here on EFGH the total unbalanced force is this. So this is getting resistance from the shear resistance which is at EF. So the shear stress along EF, if it is tau, shear stress at EF is tau, then the shear force will be tau into B into dx, and that will be equal to dm by I into A into y bar. Okay, so if we rearrange it, we will get dm dx into a y bar by I into B. Now again dm dx is actually shear force into A into y bar by I into B. So this is the expression of shear stress at a distance of y1. Here if you look, EF at a distance of y1 from neutral axis. So we have made the expression of shear stress generated at a distance of y1 from the neutral axis. Now this formula we are going to require in solving problems. So this A into y bar is the moment of area A, moment of area A about neutral axis. Okay, so let us have an example. Let us have we are going to going for example. Let us have a beam which have a cross section is like a isosceles triangle. Isosceles triangle where is B, C, D, and it is given that the shear force F is 30 kilonewton at a section where base width is there shown. That means CD is 150 mm and height is 450 mm. Okay, and our job is to determine the horizontal shear stress tau at neutral axis. Number 2, the distance from the top of the beam where the shear stress is maximum. So distance from the top of the beam where shear stress maximum. And number 3, we have to find out value of max shear stress. This is our problem. So its neutral axis will be at a distance of h/3 from the bottom. So our first job is to find out tau. Now this distance is 2h/3 into 1/3. So let us continue. Our first job is to find out the neutral axis. The neutral axis will be at a distance of h/3 from CD, and thus it will be having a distance from NA, having distance from B is 2/3 of 450, which is 300 mm. Now the length of NA from here to here can be found out from the triangle's law. So NA by CD is equal to 450 by NA by CD is 300 by 450 from the law of triangle. So NA is equal to 300 into CD is 150 by 450. So NA is 100 mm. Now the shear stress at NA will be given by the formula F into A into Y bar by I into B. So the shear stress will be, F is given 30 kilonewton. Or 30,000 Newton into area. Area is BNA of the triangle BNA. So half into NA is 100 into its height is 300 into Y bar. So Y bar is equal to 450 by 3 plus 1/3 into 2/3 into 450, okay, divided by I we have not found out, and B is the width of the NA, that is 100 we have found out. Now I can be written as BH cube by 36 for a triangular area. So here we can write B is the base. So it will be 150 into 450 cube by 36. Okay. So if I put the values here, you will get 1.8 185 Newton per mm square. Sorry, when you are finding out y bar, this quantity is not required. Y bar is measured from neutral axis, not from bottom. So that's why it will be just this. It will be just this. 1 by 3 into 2h by 3. 1 by 3 into 2h by 3. Okay. So y bar is only this much. So that is 1 by 3 into 2 by 3 into 450. Okay. So we'll get the value 1.185 Newton per mm square. So this is our first answer. Now for the second case, for the second problem, so we have to find out where the shear stress is maximum and the value of the shear stress. For that, we will draw the figure again, where we have named them as B, C, D. This was the neutral axis, sorry, NA. This point is N, this point is A. And let us assume at EF, at a distance x from the top, at EF, at a distance x from the top, the shear stress will be maximum. So from BEF and BCD, these are similar types of triangle. BCD, BEF, similar type triangle. So we can write EF by CD is equal to x by 450, or EF is equal to x into 150 by 450 is equal to x by 3. Now we know at section EF the tau will be equal to F into A into y bar divided by I into B, where y bar will be the distance of area A from neutral axis. Okay, so area A means area of BEF. Okay, so A is the area of triangle BEF, and y bar will be the distance of CG. So the CG of triangle BEF to distance of CG of triangle BEF to neutral axis. Okay, so the area of triangle BEF is equal to half into EF into the height x. So half into x by 3 into x, or x square by 6, that is the area. Now y bar will be equal to 2h by 3 minus 2x by 3. So we need this to this, that is y bar. So this is 2h by 3 minus this is 2x by 3. This is 2x by 3 and that is 2h by 3. So between the distance, that is y bar. So y bar equal to 2h by 3 minus 2x by 3. Okay, when h having a value 450, so 2 into 450 by 3, minus 2 into x by 3. So it will become 300 minus 2x by 3, and moment of inertia I of the total section of the moment of inertia of the BCD, moment of inertia of triangle BCD about NA, which will be equal to BH cube by 12, that is BH cube by 36, from neutral axis. So BH cube by 36, that we have already did in our previous problem, and here the B will be equal to EF will be equal to x by 3. Now while we put all these values in this impression of tau, then it becomes 30,000 Newton into A x square by 6 into y 300 minus 2x by 3 divided by I into B, where I is 150 into 450 cube by 36 into B. B is x by 3. So upon solving this, we will get 0.0000395 into 300x minus 2x square by 3. Okay, so for maximum tau, we have to make d tau dx is equal to 0. So if we do that, what we will get is